This is a screencast for section 2.8, example 10. We're going to be designing a juiced can again. The Stewart Cannery will package tomato juice in 2-liter or 2,000 centimeter cubed cylindrical cans. Find the radius and height of the cans if the cans have a surface area that is less than 1,000 centimeters squared. So for these 2,000 centimeter cubed cans, we're going to refer to section 2.7 example 7 to find the formula for the surface area. So here it is. We found that the surface area was 2 pi r squared, the circle on the top and the circle on the bottom, plus 2 pi r times this expression that we used for H, because the volume of this can is 2,000 milliliters. So I'm going to take this expression and drop it into our notes for today for surface area. So we'll call that S of R, actually. Surface area as a function of radius. So to simplify that function, I've got 2 pi r squared plus, let's see, 2 times 2,000 is 4,000, and then the pi's would cancel and one of the r's would cancel. So there's our simplified surface area formula. And this problem says that our surface area is less than 1,000 centimeters squared. So I need 1,000, and that's going to be the biggest value. The surface area actually has to be less than 1,000. So here we have the surface area is less than 1,000, or 1,000 is greater than the actual surface area. Either one works. So we need to find the radius and height of the cans. Well, my expression for height is right there. So once I use my calculator and find the radius, I'll be able to find the height as well. So after graphing on my calculator, I put in y1 1,000 and I put in y2 the expression we have for surface area. The actual surface area, the curve, will be below the y value 1,000, anywhere between 4.62 and 9.54 centimeters. So the radius has to be anywhere bigger than 4.62 but less than 9.65. So that's the intervals for what the radius could possibly be. Now I need to plug those both in to the formula for H to find out what H could be. And I'm actually going to use my calculator to help me find those exact values. So since my graph is on the intersection, I can now use that X value in my main screen of my calculator. So I'm going to do 2,000 divided by, and then in parentheses, pi x squared. Close those parentheses, hit enter, and I get 29.83 centimeters. And then with the intersection value of the x value of the intersection of the other point, I'm going to do the same thing. I can just hit second enter, and your calculator now knows that the new x value is from the other intersection. So I get 6.83. So the height, the range of the height values are 6.83 centimeters to 29.83 centimeters. So now I have the possibilities for my radius and height to make this can's surface area less than 1,000 centimeters squared. The now try problem is number 61. We're going to start from scratch on this one. The Flannery Cannery packs peaches. That is so bizarre. Flannery Cannery packs peaches. All right, in 0.5 liter cylindrical cans, which is 500 milliliters. So we need to express the surface area S of the can as a function of the radius X. I don't know why I didn't use R, but whatever. So surface area as a function of X. So it's not going to be a function of X yet. So I'm just going to call it S. That's going to be 2 pi r squareds, the top circle and the bottom circle of the can, plus the circumference times height. So that's 2 pi r h. So I need to figure out, I mean, it's easy to change the r's to x's, but h has to be expressed as a radius. So the other thing I know about this can is the 500 milliliter volume. So the volume of the can is pi r squared times height. The volume is specifically 500 milliliters. So when I divide both sides by pi r squared, I get that h equals 500 over pi r squared, and I can plug that in, and I'm also going to then replace everything as every r as an x. So s of x equals 2 pi x squared plus 2 pi x times the expression for h using x, 500 over pi x squared. And I can simplify that if I wanted to. That would be 1,000 over x. I'm going to do that. I'm going to push this off to the side because I can. And I'm going to say this is 2 pi x squared plus 1,000 over x. Part B says find the dimensions of the can if the surface area is less than 900 centimeters squared. So that's going to follow the strategy we did in the example, and we're going to put in y1 900 and then in y2 our expression for surface area that we just found. So after graphing, I found that the first x value, the first radius is 1.12, what are we dealing with? Centimeters. So now I'm going to use that 1.12 to find the height. Now the expression we found for height was 500 divided by pi r squared. So I'm going to take 500 and divide it by parentheses pi x squared, close parentheses. And the height that belongs to that is 126.66. The other r value I found, or technically x value, was 11.37 centimeters. So that's my maximum r value I could use. So the height to belong with, or to go with that radius is, drumroll, 1.23. Oh, 123. Oh, how cute. So the dimensions of the can, if the surface area is less than 900 centimeters squared, the radius can be 1.12 to 11.37, not including those, because those would make it not less than 900 centimeters squared, but exactly 900 centimeters squared. The height can be 1.23 centimeters. Oops, just 1.23. We'll put centimeters up there, to 126.66, also centimeters. Part C, find the least possible surface area of the can. Least sounds like minimum to me. So I'm going to take my calculator, go back to the graph, and second calc min. So I found with my calculator the least possible surface area is not 4.3. Remember, 4.3 represented the radius. The surface area was the y value, the output. So that would be 348.73 centimeters squared.